Select the best reagents or set of reagents to accomplish the following transformation. So if we take a look at our starting material, we see that we have a ketone. And if we look at our product, we still have the same ketone, we still have the same carbon chain. What we have done is we've replaced one of these two alpha hydrogens. So we had two there, now we have just one. We've replaced one of those with a bromine, a halogen. So what we're looking at here is an alpha halogenation reaction. So alpha referring to being the position 1 over from a carbonyl. So alpha halogenation. And specifically it's of a ketone. And the same conditions would also work for an aldehyde. All right, so when you look at your alpha halogenation section, you're going to see that you have two choices. So you can do this reaction under acidic conditions. And under acidic conditions, that would be having your halogen and H3O+. Or this reaction can be done under basic conditions, which involves having your molecular halogen again and an aqueous solution of hydroxide. So these are the only two conditions that we should be considering here. So we should just be considering C and D. So A and B are different conditions. In case you are curious, these are conditions in A for alpha alkylation. And the conditions in B are conditions for alpha halogenation of a carboxylic acid. Okay, so that's what those are, but we don't need to consider those. In this case, we're just looking at C and D. So the difference between acidic conditions and basic conditions for an alpha halogenation is control of the reaction. Control of the number of halogens that you are adding. So here's the key difference. Under acidic conditions, you can control the reaction to add just one halogen. So just one halogen atom. Okay, under basic conditions, you can't control this reaction. You will replace all alpha hydrogens with your halogen. So with that information, then we know that C would be the best set of conditions in order to control this reaction. So this is what we're looking at. That's going to work the best. But while we have this example here, let's go ahead and look at how this mechanism works. So I'm going to draw the mechanism for C. So you have your ketone. And I'm going to draw out that alpha hydrogen so we see where it is, because this is the one we're going to replace. But what we need to do first is we need to make this carbon into a nucleophile. So what we're going to do is we're going to convert our ketone into the enol form. So if we've got H3O+, we are going to protonate that carbonyl. So your carbonyl oxygen is your base. And it's going to grab that acidic hydrogen and break that hydrogen-oxygen bond. So now we've got the protonated carbonyl. So this is the exact opposite of the enol to keto form tautomerization that we saw in another example. So we've got that form, and then we've got this protonated, I should say. And now we can remove the alpha hydrogen. So under acidic conditions, you have to protonate first. And now we can deprotonate, and so the only base you would have in this solution would be the water, which is the conjugate base of H3O+. And so we can remove this hydrogen and form the enol. So your enol, the reason why we need this is the form that is nucleophilic at that alpha hydrogen, so that we can explain how that we functionalize this alpha carbon. Okay, and so we could protonate it, right, and go back to where we started from, but a small amount of this at least is going to react with the bromine, and this is the reaction that we're looking for. So this is how your alpha halogenation takes place. So your bromine is your electrophile, and your alpha carbon here from the enol is the nucleophile. right? So we're coming back down to reform that double bond, and we're going to break the bond between the bromine and the other bromine after we have attacked. So then we have still a protonated carbonyl. We have a CH, we've added one bromine on there, and then we have a CH3. And so we can use the water again. If you're in aqueous acid solution, you have this all surrounded by water molecules. And so we can remove that proton to get to the product. All right. And so we are able to control that reaction under acidic conditions. That's the mechanism under acidic conditions. So we set up here that we cannot control this mechanism under basic conditions. So let's take a look at why. So basic conditions involves first deprotonating. So here is your basic conditions. So you have the same starting material. And so now your first step would be to take your base, which would be the hydroxide, and remove that proton. We would form the enolate, because it's the anion. And so I chose to draw the more stable form of the enolate, which shows that negative charge on the oxygen. If you wanted to, for clarity, to see that this carbon is the nucleophilic carbon, you could just go ahead and use the resonance form that shows the electrons on that carbon atom. And either would be fine. They're both valid resonance structures. Okay, and so now this enolate could attack your bromine in the same kind of fashion that the enol did in the acidic mechanism. So we will see this coming down. We're going to swing these pi bond out to attack the bromine and break the bromine-bromine bond. So going well so far, looking like the same product. But let's draw this product here. So here we have it. We've added the bromine to the alpha position. So why is it that we can't control the reaction? Here's the problem. We've got another hydrogen here that's still attached to that alpha carbon, and this hydrogen is more acidic than this one, the one we started with. So as soon as you introduce any halogen, you've got something that's more reactive to base than your starting material. So the reaction just keeps on going. So this proton is more acidic than the alpha proton in your starting material. So then in your starting material. So that's why we can't control this reaction under basic conditions. So if you're trying to use this alpha halogenation in a synthesis, you most likely want to add just one halogen. So you're going to see that these acidic conditions are the ones that are used.